going to be lecturing today and tomorrow on learning in games, and I gave a pretty extensive motivation for this last night. Probably many of you were there, so I'm going to go very quickly over that and get to filling in all the missing details. But just to briefly set the stage, the question we're looking at is when and why does play lead to equilibrium? What sort of equilibrium? Reminding you that rationality or even common knowledge of rationality isn't sufficient as an explanation for equilibrium. Not sufficient because in games with multiple Nash equilibria, there's no way that rationality alone would explain why people coordinate at the same equilibrium. It's not necessary theoretically because we can write down the replicator dynamic, which assumes no rationality, and in some games it converges to Nash equilibrium. And it's not necessarily empirically. Convergence of Nash equilibrium has been observed in colonies of bacteria, who presumably aren't so rational. Yet it seems a decent approximation of the outcomes of some but not all static game experiments. Emphasize experiments because testing equilibrium on field data is very tricky. We don't have enough control over the payoff functions and information, and we see some variation. We don't know if the payoffs are changing or if play hasn't converged or what. Here's some of the pictures I showed you last night of play converging to equilibrium in some experiments. So at least sometimes play converges to equilibrium. And aside, those pictures are both about static game experiments where people's strategies were actions. The learning problem in extensive form games seems harder, not just theoretically but also empirically. And in extensive form experiments, it's less obvious we've converged to equilibrium. Guillaume mentioned my work with Anna Draper and Dave Rand on the repeated prisoner's dilemma with imperfect public monitoring. What he didn't point out is that in the treatments we ran with a high reward to cooperation, where most people cooperated, still, at the end of the experiment, it's about 20% of the people who were playing defect all the time. Okay? Now, different people playing different strategies on its face is not inconsistent with Nash equilibrium if all the strategies get about the same payoff. It could be approximating a mixed equilibrium. But in this case, the people playing always defect were doing markedly worse than the people who were playing conditionally cooperative strategies. So, if 5% of the people aren't doing well, that's just random noise. Any experiment will have that. If 20% of the people are doing much worse than everyone else, we at least need to stop and think whether that's, close enough to equilibrium to say the plays converge to equilibrium. And this is just an example that I know well. This is true in many other of these extensive form experiments. To understand how and when equilibrium arises, we're going to look at the long-run behavior of non-equilibrium dynamic processes. Well, what kind of processes? And what does learning mean exactly? Many sorts of processes have been said to involve learning in a broad sense. And it turns out to be hard to draw a bright line saying this is a learning model and this isn't. The replicator dynamic is motivated by evolution, but it's also been justified as a result of imitation by human agents. Is that learning or not? So who knows? Think of a model where each period everyone observes the current distribution of strategies and plays the best response to it when it's their turn to move. So they're adjusting. Are they learning anything? They see everything. So maybe that's not learning. But what if instead of getting a perfect sample, a perfect signal of the current state, everyone gets a noisy signal of a current state? Is that learning? Or if you get a signal that depends on the state today and yesterday. So it's a gray line. I'm not going to try and give you a formal definition. These are learning models. These aren't learning models. That doesn't seem productive. Today I'm going to focus on a fairly narrow sense of learning. So unlike, say, in the replicator, which starts out at the aggregate level, I'm going to start out specifying the behavior of individual agents. Say how individual agents use their observations to change their behavior. I'm going to assume self-interested play on the part of the agents. So these won't be agents who are trying to get to equilibrium. That's somehow part of their objective. It's trying to maximize their payoff. And the rules I'll look at are going to be uncoupled in the sense that Sergio used yesterday. We're going to not let player 1's rule depend on the payoffs of player 2. Some common themes in this literature. Non-equilibrium adjustment. What do I mean? Well, it's pointless. If I want to explain how to get to equilibrium in Battle of the Sexes, I could write down some big dynamic game, say, well, people have rules and big dynamic adjustment game, let's look for an equilibrium in the big game. If we want to understand equilibrium, it seems perverse to explain equilibrium in a small problem by assuming equilibrium in a big problem. It just pushes the question back to a harder level. That's sort of an obvious point, but I emphasize it because it has a consequence. If you accept that we won't insist on equilibrium in the overall dynamic game, then we have to accept that some player must, or we have to allow for the possibility that some player is, quote, making a mistake. Meaning what? Meaning some player's rule in the dynamic game might not be the best possible rule given the rules of everyone else. Why? Well, if we negate that, we're back to equilibrium. So if we accept that equilibrium, people might make mistakes. So simply pointing out, if I write down a family of rules, pointing out, oh, this guy could do better by changing his rule, I'm not going to take that as a very interesting comment. Okay? That's just not the point. On the other hand, that's not to say that any rule, no matter how silly, is fair game. Instead, we're going to allow for mistakes, but we're going to insist the mistakes be quote-unquote plausible, but they not be too stupid, so stupid people would spot them. Now, that's not a technical term, so it's going to be a judgment call about what sorts of mistakes we think are sensible and what sorts we think people would detect. Another feature of my talk and most of this literature is going to be focused on long-run play, on the asymptotics. Okay. Good reason not to focus on the initial play, which will be totally driven by the priors. There's no chance to learn at the start. It would be nice if we knew more about medium-run play, about how fast play changes, what would happen over some sensible time frame. It's sort of hard to quantify, even define what we mean by a medium term, let alone have results. So there aren't good results there. I wish there were. It's sort of an open problem. Another thing we'll need to keep in mind if we start writing down dynamic processes we think are a priori well motivated, there's no reason to suspect that they will guarantee that they will converge in all games. It's not a general property that all dynamic processes converge to steady states. Right? They could cycle, they could be chaotic, many things could happen, so we shouldn't take convergence for granted. Another feature of these models, our players are going to be playing repeatedly without playing a repeated game. And to motivate this, I want you to think of anonymous random matching as in experimental economics. So they're not playing a repeated game, but they could repeatedly play a repeated game as in Guillaume's experiments. So what you're learning how to play is a repeated game. You play the repeated game many times. Of course, the outcome of learning depends on what players observe. And we'll be varying that a bit in the talks. It also depends on whether their actions change what they get to see. If the actions don't change what they see, I speak of passive learning. You're just passively watching signals, deciding how to respond. If your actions influence the signals, I call that active learning. So today will all be passive learning. Tomorrow will be active learning. Okay, what criteria should we use in picking the learning rules to analyze? Well, if I could ask Guillaume, hey, go to the lab, Guillaume, and work out exactly the rule people use. Okay, to have the rule, problem solved, we just use that rule to make all predictions. Or more realistically, he wouldn't tell me, here's the rule. He'd say, if you have 100 subjects, 20 use this rule and 15 use that rule and whatever. We're nowhere near that level of knowledge, and we won't be for a long time. It's just too hard to pin down individual level behavior. There's too much noise. So we need to use some intuition and prior beliefs in picking the models. And we also are going to, being theorists, going to tend to favor models that are simple and easy to work with at the cost of some accuracy. We're not going to try and fit every last detail of learning, look for models that capture the broad features and still let us get some long-run predictions. Okay, that's may sound sensible. Of course, the devil's in the details. How am I going to do this? And what criteria am I going to use in picking the learning rules? And there's different criteria used in the literature. One of them is to say that we're going to evaluate rules by their worst case performance. How well would they do in the worst possible case, a sort of min-max against nature criterion. And Sergio is going to be talking about that, I think, later this morning. At least the last I heard from him about his plans for today. That's what he was going to be talking about. A different approach that's more familiar to most economists and economics grad students is to suppose that agents, are savage rational, they're Bayesians, they're maximizing discounted expected utility. Okay, so with some prior. Another approach is to write down exogenous rules that are quote-unquote boundedly rational. And here by boundedly rational, all that I mean is we write them down as opposed to deriving them. Okay. So this is really a difference as much in methodology as in content, because it turns out that Bayesian rationality has very few restrictions if you are sufficiently creative with the priors and likelihood functions. So it may not be obvious looking at a rule whether or not it has a Bayesian rationalization. Okay? So, and we'll see an example of this where actually it is fairly obvious. I should also say, please feel free to stop, ask questions or whatever, debate. Please, louder. Yeah, so passive learning is you are sitting on the side, each period a signal comes, you see the signal, you try and interpret it. Given your beliefs, you do something, but what you do has no influence on the distribution of signals. It's going to be the same signals no matter what you do. Active learning, in picking your action, it may change the distribution of signals. So then you may have a trade-off. You may say, gee, well, this action I think will probably make me more money today, but this other action may give me more information that could help me in the future. And then you might not pick the action that maximizes today's money if there's enough to learn about what's going on. So that's the distinction. And today we're doing the passive learning case. Okay. So that's overview of the kind of rules. Here's a particular rule I'm going to start with. It's called fictitious play. Sort of a funny name. Why am I doing predictive game theory, with the name, about fantasy? Well, because this is sort of a history of the concept. It was introduced by Brown as a way to compute equilibria in two-player games. So he didn't think of it as a way of making predictions. Hence, and he called it fictitious play. I'm going to tell you what it is, and I'm going to claim it can be used as a simple and stylized model of learning. It's pretty easy to analyze and motivate. It's too simple to be a good fit for experimental data, but it's a foundation for more complex models. We can add some tweaks to this and make it perform better. Okay, the motivation for this learning rule, suppose the agent is going to repeatedly play a fixed, static, strategic form game in the lab. Okay? The agent knows the payoff matrix, the structure of the game, but does not know what the other side is going to do. That's what he wants to learn about. All the agent observes is the outcome of play in their own matches. Each day you play the game, say about you play A or B, you see what your partner does. You don't observe what happens in other matches, and you don't observe what your current partner did in past matches. Okay? Now suppose the agent believes that he's playing against a random sample from a big population, which is what we want them to believe in the lab, and does not try to influence opponents' play. That's what I mean by strategic myopia. So the converse of this would be if we put people in a fixed pair, or there's only 4 people in the lab and you're matched every period, so you probably half you play the same guy again, now there is a reason not to be myopic. You might want to give up money today to get the guy to play differently tomorrow. But with a large population random matching, you're strategically myopic. Even if your discount factor is not 0, there's no point in giving up money today to change what this guy sees. Also in this setting, we have a justification for the assumption of passive learning I was talking about. Because what the agent sees is independent of own action. He has no reason to change his play to change his information. Okay. Next assumption, Edward. Strategic form games, yes.
Can I think of these also as a, So can it be an extensive form game? I transform it to a strategic form game?
If you transform it to a strategic form game, and when the game is played, you tell player 1, player 2's complete strategy, then yes. Now, let me finish. So that requires, then the lab requires you actually use the strategy method. You can't have them play the game online. Player 2 would have to commit to a complete plan, and you'd have to tell it to player 1. So I would say once you've done that, it's no longer an extensive game. It is a strategic form game. It's a one-shot simultaneous game where people pick strategies. Okay. If it's really an extensive game, and you don't make people pre-commit to their strategies, you don't have the data to tell player 2 what player 1's strategy is. Even you don't know it.
But does this passive learning story still?
If we transform the extensive game to a strategic form game, and then tell player 2, player 1's strategy and vice versa, then it still holds because it's the same setting. It's not a different setting. If we transform it to a strategic form game, it's a strategic form game.
But I still have the incentives to, say, play differently, to choose a different strategy to see other...
No. So we have a strategic form. Okay. We tell player 2, write down your complete contingent plan. And at the end of each round, we tell player 1 what player 2's complete contingent plan was. Then regardless of what player 1 does, he will see player 2's complete contingent plan. So there's no reason for player 1 to change his play to learn things. That's exactly the point. Is good? Okay. The next assumption, agents act as if they're Bayesian expected utility maximizers. It's not so boundedly rational here, facing a stationary but unknown distribution of opponent strategies. So stationarity, I assert, is a reasonable first hypothesis in many situations. If you don't know better, you might think the world is stationary. And you might think players to stick to it if it's approximately right, but to reject it given sufficient evidence to the contrary. So if there's a strong time trend, if you see 10, 9, 8, 7, 6, 5, 4, you wouldn't take the average. You'd predict 3. Or if you see a 2 cycle, the heads, tails, heads, tails, heads, tails, you might not believe in stationarity. But if you see things that look roughly stationary, you might believe stationarity. Stationarity implies that all observations are equally informative and that beliefs are asymptotically empirical, that they converge to the empirical distribution as the sample size grows. So this is an assumption of this model. Now, as I mentioned last night, at least in some cases, people give less weight to older data, displaying what's called recency bias. And when they do that, this stationarity is not a good assumption. So let me just have a brief aside on recency, and then I'll go back to fictitious play. So there's a large psychology literature looking at recency in decision problems, certain class of decision problems. One reference for this is the Handbook of Experimental Economics. There is some work in learning in games that allows for recency. Bonheim, Hofbauer, and Hopkins look at a variant of fictitious play. So what I meant by fictitious play is a building block for more complex things, when agents have vanishingly little recency bias. Let me finish this bullet point and I'll take the comment. So what I mean by this, they have a model where for each level of recency, there's an ergodic distribution. And then they characterize the limit of the ergodic distribution as the recency bias vanishes. Okay? That ought to be a close paren there. Okay, please, in back. Louder? The recency and? Well, extrapolation, I guess I don't know what you mean by extrapolation. There are many rules I could use to extrapolate the next action. I think of extrapolation as a synonym for prediction. So suppose I predict the distribution of play tomorrow equals the empirical average of what I've seen before. Is that extrapolation? It's a kind, but no recency. So recency is a particular kind of extrapolation where you give more weight to yesterday than 10 periods ago, say. Okay. Sergio is going to be talking about notions of consistency today, which is a sort of worst case time average rule. Dave Levine and I have a paper that extends these sorts of calibration or consistency results to the case of recency. But as here, our results only of interest in the case of very little recency. It holds for any level, but it's sort of not very interesting otherwise. On the other hand, empirically, Alex Pesakovich and I have a paper, an experimental paper, that documents a case where people have, quote, a lot of recency bias. Okay? So then this taking the recency going to 0 is not a good approximation of our data. So that's sort of awkward. What do you do about that? You know, the Benheim-Hofbauer-Hopkins model is, they don't really tell us what happens for any given level of recency. It's very hard to get nice predictions. Alex and I worked on a particular adaptive model and did simulations to get predictions. It's hard to get analytic results. We also found that the amount of recency in the lab could be diminished by varying the feedback we gave the subjects. If we gave them records of past play and sufficient statistics, and averages of past play, some summary statistics, then there's a lot less recency. Now, Guillaume. Yes, very much so. It's, yes. Yes, so that's, there's, I don't know of any evidence in the lab that best respond to yesterday. People overreact to yesterday, best respond to yesterday in a deterministic, especially in a deterministic world. So I should, both this Lemon's problem, most of the other psych stuff is on settings where the stage game has a move by nature. It's inherently stochastic. And that's part of what's going on. People have a hard time dealing with the probabilities. If it's in Cournot, yeah, I think you'd see some recency, but nowhere near the amount. So in the Cournot game, if you did it, you see more like Chung Friedman levels of recency and not Cournot's level of recency. Okay, so recency is a real thing. How big a thing depends on the setting. It's hard to deal with. People are starting to. Let's assume it away for now. Okay? Please.
Are those conclusions verified also by real life empirical?
As I said, it's hard to say, it's hard for me to say much about field data in game theory because we don't know enough about the payoff functions. I just don't know. There's not enough controls. Some people try and people use game theory like in I/O to do estimation. Their equilibrium is usually a maintained assumption. They're not testing it. They use that to estimate parameters. In auctions, people say equilibrium imposes some inequalities on things. People test the inequalities and equilibrium directly. So I think it's very hard to tell how well things do in the field, and I'm simply not going to talk about it. I'm talking about, if I talk about data at all, it will be lab data. Interesting thing, I'm not talking about it. So fictitious play, no recency. Asymptotic empiricism.
You had a bullet point you didn't talk about compilation. The economies that need to work out how to make very.
Yes, I agree. No, this is exhortation. It's cheap talk. Okay. This would be a good thing for people to do. We don't know how to do it well. We don't have criterion for judging it. I think you can't do a simulation on one parameter set and then spin a story and be done. But how many different parameter sets do you need to look at? How do you use simulation systematically to convince people that you've understood a phenomena? I don't think we know how to do it. We certainly don't have norms for it. So both, I don't think we do it well, and the journals have no way of evaluating it. So it's a problem. But this is more. So I would encourage people to try and think about this and try and do this. So ignore recency. Asymptotic empiricism. That still doesn't really give us a concrete rule. Fictitious play is a particular concrete rule where you start players off with initial weight functions. They give a weight to each opponent's strategy. You add 1 to the weight of each opponent's strategy each time it's played. And the probability that player I assigns to player not I playing strategy S not I is the weight on that strategy divided by the sum of the weights. So fictitious play is going to be defined as any behavior rule that computes beliefs in this way and then picks a best response, picks an action that maximizes expected payoff given those beliefs.
Everyone doesn't see strategies as an action.
I'm looking at strategic form games where actions, one-shot simultaneous games where action equals strategy. So player 1 does see strategy. Tomorrow, player 1 won't see strategy. Today, player 1 does see strategy. So this looks like an arbitrary rule. What, Eric?
Do you include randomizations over best responses?
In the classic fictitious play, no. So if it's a tie, you pick a best response. So it's any rule that picks a pure best response. So this rule, which Brown just wrote down as a computation aid, has a Bayesian interpretation. So as I said, this belief thing where you have weights, you add 1 each time, that's exactly Bayesian updating if you think the world is stationary. And if, in addition, your prior takes the form of a Dirichlet distribution. So the Dirichlet prior and the multinomial data forms a conjugate family. You update with a draw, you get exactly this. If you're not familiar with this, the details are at the end of the notes. This is textbook material. I copied this out of de Groot's 1970 textbook on statistical decisions. So is fictitious play boundedly rational or not? I mean, Brown wrote it down to compute stuff. We can just specify it. And then after it was written down, it was noticed, oh, look, this is actually Bayesian. So let's say there's no bright line. The key conceptual point that I want you to have in mind thinking about these models is that the belief a player has about the distribution of opponent's play today, what's the probability my opponent plays heads, is the expected value of beliefs over mixed strategies in the population. Okay? So updating from today to tomorrow depends on more what you think is going to happen today. So here's 2 different situations. One is, I'm sure my opponent plays a half heads, a half tails. So your prior is a point mass on 50-50. Then you expect today's play equally likely heads and tails. But you also expect, even after seeing today's play, tomorrow's play is 50-50 heads, tails. And the day after tomorrow, after any history, you expect your future beliefs will be 50-50 heads, tails. You don't expect to learn anything. On the other hand, your prior might have a 2-point support. 0.5 on my opponent always plays heads. 0.5, my opponent always plays tails. That is exactly the same consequence for belief today. What's he going to do today? 50-50 heads and tails. But the learning implication is different. Because now you think whatever he does today, he'll do tomorrow and the next day and the day after that. Okay? So we have a distinction between your point prediction of play today and the belief over the distribution in the population, which is a more complex object. Brown's fictitious play has these weights. You add 1 each time. That corresponds to a particular prior, this Dirichlet prior. So that's convenient for calculations, have this nice functional form. It's not needed for many of the results. Okay? For at least the first results I'll show you, all we need is this assumption that the player treats the world as stationary, so their beliefs are asymptotically empirical, and that players, at least asymptotically, are myopic and play a best response to their beliefs. Okay, in a bit I'll relax this asymptotic myopia to allow random choice that fits some data better, has better long-run properties. in any Bayesian scheme, your point prediction for play today will differ from your data because you have a prior. But over time, data swamps the prior. Fictitious play beliefs are based implicitly on the assumption that you think the world is stationary. If the process cycles or has a time trend, people are wrong.
I assume that the evolution of the process is very dependent on which initial prior we impose.
Yes?
And how do we analyze that in any...
We'll see what we analyze once I show you what I've done. You can ask me about other things. If the cycles persist, we might think people would notice them. But note, this rule at least has the advantage compared to the Cournot process Guillaume mentioned, which is best response to yesterday. With that process, if you run it, play at period 1 is different than period 2 is period 3, the player's belief quickly gets falsified. He thinks the world is stationary. He thinks today is yesterday. He quickly learns it's not. If you think the world is, the distribution of play is some mixed strategy, and it's not really, well, there's no finite sample that's inconsistent with your prior. You might get suspicious after a while, but heads, tails, heads, tails, heads, tails is unlikely if it's IID, but it's not impossible. So it's at least harder to falsify than today equals yesterday. Let me contrast fictitious play to an alternative model of learning that was developed in psychology called reinforcement learning, where agents update based only on the payoff that they received. Okay? So then, because you update only based on realized payoff, players don't think about regret, which is defined as the payoff you would have gotten if you'd done something else. So there's lots of different reinforcement learning models. To define one, you have to decide what is being reinforced. Actions, strategies, rules. Different papers have different things. And how they're reinforced. And the very simplest kind of reinforcement learning is cumulative proportional reinforcement on actions. So I'm going to normalize so all utilities are positive and give initial weights to each action. And then each time you play the game, you update the score of that action by the payoff you got. You don't update the other scores at all. And the probability you give an action is its weight divided by sum of weights. Okay. Well, then, when player 2 plays, so then if player 1 sees player 2 play right, how does that change player 1's play? With this model, it depends on player 1's payoff. That depends on what player 1 did. So your response to an observation here depends on your own action. If the players are told the payoff matrix and they're rational, they shouldn't condition on their own action. There's no information in what you did. Lab subjects do seem to at least somewhat condition on what they did. So that's favoring reinforcement learning against fictitious play. On the other hand, reinforcement learning agents don't respond at all to what they could have gotten by playing something else. They respond only to the payoff they got. And people do that. Also, if you run two treatments, one where people are told the opponent's payoffs and one where you're not, people play differently. And with reinforcement learning, this wouldn't happen. So reinforcement learning isn't perfect either. It was a famous horse race. Roth, Arov, and Chung Friedman look at reinforcement learning and fictitious play respectively, each on their own data sets, and say, oh, look, our model does best on our data, we win. It's a historical note that's in Chung Friedman do include a recency term in their estimation. Kammerer-Ho nests both of these models in a more general model by adding a parameter. Okay? And this parameter allows for a different weight on the actual payoff you got and on the hypothetical payoff you could have gotten by playing something else. So extreme values of the parameter correspond to fictitious play and reinforcement learning, and to no one's surprise, when you have extreme values here and here and you estimate, the parameter ends up in the middle. Okay? So they win. The good thing about their paper isn't that they won, but that instead of looking at their model on their own custom data, they ran their model on a large set of data, their own and data from past experiments. And my takeaway from their analysis, not what they say, but looking at what all the experiments they put together, that all three of these models actually fit pretty well in cases where an agent who used any of the models would do reasonably well, which is the cases where the play is not changing very much over the course of the experiment. And all three of the models perform quite badly and don't fit well in games with a strong time trend, like the beauty contest game. Remember the beauty contest game? The winner is 2/3 of the average, and you run it, and so the average might be 20 the first time, and then 10, and then 5, and then 2. People notice there's a time trend. And so you're not going to fit this behavior with a model where people are best responding thinking that they're seeing a random draw from a stationary distribution. So that was the initial horse race. So 2 glosses on this. Salmon does something which is quite clever. Sort of he creates fake data, saying suppose people actually learned with model A, model B, model C, make a bunch of data, run the econometrics that people were using for the horse races, and said, oh, you can't tell these things apart. There's no power in the tests people are using. So that was interesting. Following Kemmerer and Ho and the other papers, he assumes that all the agents in the population use the same learning rule, which is a pretty bad assumption. People differ in lots of ways, not only their preferences, but their learning rules. So when I left off of journals, I retrofitted those. So I think both of these are econometrica. We should add that to the notes. Wilcox shows that assuming everyone uses the same rule tends to bias the estimates in favor of reinforcement learning. Okay, why is that? Because of what's called heterogeneity bias. Suppose people are different, and you leave that out. You've left out an individual effect. Well, the action I played yesterday is correlated with this individual type of mind I didn't put in the model, so then the action yesterday will show up in the regression as a proxy for my type. Okay. Onwards with fictitious play. How do we think about cycles in fictitious play? Consider this coordination game, and then suppose we play it with fictitious play with only one agent per side, or lots of people all with the same beliefs. And the beliefs have this funny, remember, fictitious play, your prior is a weight on a number on each action. Suppose we have these screwy looking rates, 1 root 2. Okay? What's going to happen? In the first period, each player says, oh, root 2 is more than 1, B is more likely than A. If B is more likely than A, I want to play A. So both people play A. Now we both saw A be played. We both update our weights by 1. Next period, the weights are 2, comma, root 2, because we updated this one by 1. So now we say, oh, 2 is more than root 2. I think A is more likely than B. Well, if A is more likely than B, I'm going to play B. And both guys play B. So the first period we play here, second period we play here, third period we play here, fourth period we play here. We have this 2 cycle. And people are getting below their min-max payoff. Right? You can guarantee a half by randomizing, and people are getting 0 every day. So you might think people would notice that. Okay? Now it's true that in this 2 cycle, the frequency of A converges to a half, and the frequency of B converges to half for each player. So we converge to 50-50 in terms of time averages, and that's the Nash equilibrium. So Brown was would be perfectly happy with things like this. He computed the mixed equilibrium. It's a bad model of learning. This isn't really because you might think that people would realize they're getting 0 all the time. Okay? So I claim that people would notice this cycle. God, I'm going slow. And for more sophisticated beliefs, we don't want to identify a cycle with its average, and we want to worry about correlations. Okay. Important facts about fictitious play. If the actions converge, they converge to a pure strategy Nash equilibrium. You can't repeatedly play the same pure thing that's not Nash because someone would learn they're making a mistake. if the time averages of the empirical marginals happens to converge, then that joint distribution of the marginals is a Nash equilibrium. Okay? Why? Well, if say 2's marginal converges to sigma 2, one's belief converges to sigma 2. Then if what one's been doing, in average, isn't a best response to sigma 2, then some S1 that's in sigma 1 is strictly better than something else, and then we'd have only this, only S1. So it's, if the time averages converge, it's Nash. And for those assumptions, we didn't need the functional form of a Dirichlet prior. All we needed was asymptotically empirical and asymptotically myopic. Another interesting fact, fictitious play, quote unquote, behaves well when there are infrequent changes of play. So we just change of play, count how often a player changes his action from one period to the next. And if that's infrequent, in this technical sense I won't read, but it's here for reference, then it does as well as maximizing it's the time average of opponent's play. And it also converges to the continuous time best response dynamic. And that's the result of Maunder, Samet, and Sela. In my example, fictitious play was doing really badly. That did not satisfy this infrequent switch condition. People were changing every period. And the requirement is that the switches have to get slower and slower as time goes on. They have to get rarer and rarer. That's what this is saying. They're increasingly infrequent. Okay. So let's talk about how to analyze the asymptotics of fictitious play. I'm going to do time rescaling. Let the empirical distribution of i's play be di super t. Then ignoring the priors, which won't matter for large t, and I'll talk a bit about how to handle them. The empirical distribution at time t is what? Well, it's t minus 1 over t times what it was at t minus 1 plus 1 over t times what happens at time t. What happens at time t? Player I plays an action, plays the best response to his beliefs. So the ignoring the priors part is saying suppose player I plays the best response to the empirical average instead of his belief. His belief won't quite be this empirical average because of the prior. And as Eric said, what happens if they're indifferent? Make a pure selection if indifferent. Now I'm going to change time units. Let tau be log t. Or let t be the exponent of tau. Why am I doing this? Well, you see with this process, it's going slower and slower. The more data you have, the less impact each data point has. So this is a difference equation, but it's not time homogeneous. It's slowing down, slowing down, slowing down. So you could hope that in the limits, it slows all the way down and it's nice and continuous. Okay? Suppose there's infrequent switches. The condition on the previous slide. So for large enough tau, play is more or less constant between tau and tau plus delta. Okay. Then claim for large t and small delta, I can approximate that difference equation by a continuous time equation that di dot is the best response to the opponent's distribution minus di. When it's valid, we can study the long-run behavior of fictitious play by studying this. This is called the continuous time best response dynamic. Right? Just eyeballing this, we can tell that steady states of this process are Nash equilibrium. What's a steady state? If this is 0, your best response is what you've been doing so far. Okay, so each player's action is best response to the opponent's distribution. And then we can use standard techniques to talk about convergence to equilibrium, stability of equilibrium, and so on. But there's some work involved in, or something glossed over here, when is infrequent switches satisfied? A easier way to get to long-run dynamics is to take this exact best response function, the BR, and smooth it out. Replace it with a smooth or stochastic best response. Okay? We have a rule just like fictitious play. You form beliefs the same way, but instead of playing a best response to beliefs, you're going to play a stochastic best response to beliefs. So think of a stochastic best response as an approximation to the best response that's continuous, and even differentiable. Okay? Some advantages of this: if we have a smooth best response, if your beliefs converge to 50-50, then your action converges to something. Right? In that screwy example, beliefs were converging to 50-50, and play was oscillating wildly from back and forth, back and forth. Here, beliefs converge to 50-50, play converges to something, some mixed action. Now we're going to, and with this sort of model, we can converge to a case where people are mixing each day. We could have convergence to mixed equilibrium, which fictitious play can't do. The standard best response function is discontinuous, right? You go from A to B with a difference point in between. So a very small change in data leads to abrupt change in beliefs. That may not be descriptively realistic. I think it's probably not. This is what led to those frequent switches in that counterexample, and so poor worst case performance where people got worse than min-max. And it makes the analysis harder because now we have to work with differential inclusions instead of differential equations, and that's doable, but it's just more complicated. There's a non-Bayesian sense that in which these stochastic rules perform better. So no pure rule can be calibrated in Sergiu's sense or consistent, but these stochastic ones can. One way to think about stochastic responses, not the only, that will be familiar to the economics grad students, I hope, is the idea of private payoff shocks a la Harsanyi. Suppose each day, each player gets some small, unobserved payoff shock. Then we can define a stochastic best response BR bar I for player I to the mixed strategy sigma minus I of player not I. That'll be a distribution over player I strategies, a probability distribution, a mixed strategy. So what probability does BR bar give to a particular pure strategy SI? The probability it gives to SI is the probability that the payoff shock A to I makes SI the best response. So your beliefs are such, you're close to indifferent between apples and bananas. Some days you have a payoff shock, you like apples. Some days you have a payoff shock, you like bananas. That's a standard payoff shock interpretation. We can also get to these stochastic best responses from models of indecision or ambiguity aversion. Okay. Now, I used to have exact best responses. And you know that Nash equilibria is the intersection of the best responses. If I start approximating the best responses with freehanding in some smooth curves, well, the intersection might not be so close to the Nash equilibria if the curves that I drew were far from the original curves. But the intersection converges to a set of Nash equilibria as the random components converge to zero. Okay, this idea that goes back to Harsanyi. Version of this is in Hofbauer and Sandholm. An observation, a different way of, is that going to matter here? Oh, fine, whatever. A different way of generating smooth best responses is to suppose that instead of maximizing utility, players maximize ordinary expected utility plus a concave function vi that's very steep at the boundaries. Meets an inada condition that keeps you from putting weight 0 on something. So if we do that and make the perturbation small, then once again the fixed points of these approximate best responses are close to the Nash equilibria. And a canonical example of this, if we perturb utility by adding entropy, we get out logit best response. I have a paper with Ryota Ojima, who's a Harvard graduate student, and Thomas Strowecki, that characterizes the revealed preference implications of this subclass of a subclass of these sorts of perturbations, and shows this corresponds to ambiguity aversion. So I was saying there's lots of different ways of getting to stochastic choice. For today, let's just take stochastic choice as given and plug it into fictitious play. So we can interpret it as random utility, ambiguity aversion, whatever you like. And now we want to say what happens. Okay? And the technical tool that we use to tell what happens is called stochastic approximation. This is a technique that's going to let us relate the long-run behavior of the thing we care about, fictitious play, smooth fictitious play, which is a discrete time stochastic system, to a deterministic continuous time system. So deterministic is easier than stochastic. Continuous time differential equations are easier than difference equations. So this is the motivation here. And I'm going to show you how to do this in settings with one agent per player role, even though this undercuts the idea that agents don't treat the interaction as repeated. So to really make sense of this, we need to have many people in a role. And at the end of these notes, I have some things about how to do that I probably won't have time to get to. It's based on our work with Takahashi. But I do want to tell you about stochastic approximation. It's important for learning in games, and it's just a good technique. If you haven't seen this before, it's a useful mathematical technique. The ideas are what? We have this system with step size 1 over t and shocks. Okay? Well, the shocks have bounded variance, so we expect the average of the shocks ought to go away from the law of large numbers. That's half the intuition. That gets rid of the stochastic part, and we get to continuous time by the kind of rescaling that I showed you a few slides ago. The thing is slowing down, and so we can get to continuous time by rescaling. So here's a more formal version of this. Consider a discrete time stochastic process on a compact set in Rn. Theta t plus 1 minus theta t, that's the step size, is given by f of theta t. That's sort of the main expected motion, plus eta t plus 1 plus bt plus 1 over t plus 1. So the step size is of order 1 over t. These eta t's are noise term with mean 0. So they're mean 0 noise terms. And they're going to have the usual sorts of bounded variance and maybe bounded third and fourth moment conditions, depending on the proof. And these bt's are nuisance terms that needn't be mean 0, but they converge to 0 almost surely. And this is where we're going to sweep in things like the fact that the priors matter, and people aren't playing a best response to the empirical, they're playing a best response to their beliefs, which are close. Okay? Important thing to note in this setup, these noise terms eta t needn't be independent or even exchangeable. So all we need is that they are mean 0 and bounded moments. And it's important because in our applications they won't be independent or exchangeable. And we want to relate that complicated system to the simpler system, theta dot equals f of theta. So ignore everything but the expected motion. So intuition for this in an example, let's look at a special case. Suppose our state space is just minus 1, 1, f of 0 equals 0, and theta f of 0 is less than 0 for theta not 0. So what does that mean? It means if theta is negative, the thing is going up. If theta is positive, the thing is going down. So if we looked at this intuitively, we're pointing in towards the middle. So we'd expect the system to converge towards 0. Looking at the continuous time system, 0 is globally stable. It's very easy to see. Okay? So the general theorem that I'm going to state reduces to the conclusion that the discrete time system converges to 0 with probability 1. Why might that be true? Well, looking at the continuous time system, you'd say, oh, maybe we could use a Lyapunov function, v of theta equals theta squared. And in continuous time, this thing is always shrinking, so that's a proof of global stability. But when we go to the discrete time system, we have a problem this v, the analog of being a Lyapunov function would be a supermartingale. It should be getting smaller. It's not a supermartingale. If we're right at 0 currently, the noise is going to maybe move us away from 0. So the expectation of v of 0 is more than 0. Okay? On the other hand, if we're, say, at minus a quarter, okay, and time is really big, then the noise isn't going to have much effect, and v will tend to increase. Outside of any neighborhood of 0, we expect that outside of any neighborhood of 0, we can find a time t where for big enough t, v is going down in expectation. So it's sort of almost a supermartingale. It gets closer and closer to 1 as t gets bigger and bigger. Okay? So that's why you might hope that the discrete time system is also converging to 0. And it does. So let me go back to the system. First thing we want to say is that almost surely the realization of the sample path is an invariant set of the continuous time process theta dot equals f of theta. I'm going to show you a theorem on the next slide. There's a bunch of technical terms. I don't want to take the time to define the technical terms, things like omega limit and flow and so on. So they're here for reference. So if you can maybe guess the meanings by context, and if not, you can look them up because the slides will be posted. So assume this function f is C2, that the expectation of eta t plus 1 given h is 0 almost surely. The noise term eta has uniformly bounded variance, and the b's converge to 0 almost surely. Then the result of Bonheim and Hirsch, GB99, is that with probability 1, the omega limit of any realization is an invariant set of a continuous time process. And this set is compact connected and contains no proper subsets that are attractors for the continuous time process. So in the jargon of this literature, it's internally chain recurrent. Okay? So we've just said we can say something about where a stochastic process ends up by looking at the continuous time process. So Bonheim-Hirsch didn't quite state the theorem I showed you. They didn't have this nuisance term Bt. You can add it in without much trouble, so the same proof works. As a consequence of that, if it turns out our stochastic system ends up in a cycle, that cycle had better be a closed orbit of the continuous time dynamics. If our stochastic system converges to a point, that point had better be a steady state of the continuous time dynamics. Okay, so we already know a lot from that proposition. In addition, they show that the noise will eventually kick the system away from any unstable states. Right? Our continuous time system could have a steady state that's unstable. And okay, intuitively, if it's unstable, it shouldn't stay there. With noise, we can make that formal. The noise will kick it out. And they have a theorem on that I've elided from these notes, but you can look this up. So you need to have some noise. So, and then the theorem is if the state's linearly unstable, has a positive eigenvalue in some direction, you can't stick there. So that's the general result. In application of smooth fictitious play, the state space is just the empirical distribution. How often is player 1 played left-right? How often is player 2 played left-right? And this map F is just this continuous time best response dynamic, BR bar of theta minus theta. The noise term is the difference between this, between the expected value of this, say 2/3 heads, and what happens. Right? Your BR bar might say 2/3 heads. In actuality, either you play heads or you play tails. So the realization is not the same. That's the noise term. But this noise term has expectation 0. So by construction, we just defined it to be the difference between the mean and everything else. It needn't be IID or even exchangeable. So illustration, 2 players, 2 actions each. Now I can For each player, I can describe their history of play with one number, because it's 2 actions. So my state space is 2-dimensional. Okay? Theta I is the fraction of time I has taken its first action in the continuous time system. And the theorem says we can study long-run behavior by looking at this theta dot equals BR bar of theta minus theta. And in my 2-dimensional case, it's BR bar 1 of theta 2. This is how player 1 responds to theta 2 minus theta 1. This is what's happening to the distribution of player 1's play. And this should be a vector. Don't know what happened with the stacking there. Think of this as a column vector. BR bar 2 of theta 1 minus theta 2. More generally, the mean field is just this smooth best response dynamic. And again, Van and Hirsch said that smooth fictitious play converges to the Nash distribution. That's the intersection of these smooth best response curves. In any game where this Nash distribution is a global attractor for the continuous time dynamic. Okay. So how do you show that it's an attractor? You could build a Lyapunov function, okay. So that's true in some games. This theorem can't apply to 2x2 games like Battle of the Sexes, that have 2 pure equilibria and 1 mixed equilibria. What will happen then? Well, in continuous time, not so many things can happen in dimension 2. We can have convergence, or we can have a cycle. They show that it can't cycle, that smooth fictitious play can't cycle in 2x2 games because it's volume contracting. So if you have to go to a cycle or a steady state and you can't go to a cycle, you've got to go to a steady state. So Battle of the Sexes, we're going to an equilibrium. Proposition, if every strategy profile has positive probability at every state, that's the condition on these smooth best responses. You always have some probability of playing A even if B looks better. Or in the random utility model, there's fat tails on the support of the noise. And theta star is an asymptotically stable equilibrium of the continuous time process. Then there's positive probability that we converge to theta star. On the other hand, the mixed equilibrium is unstable. So we're going to end up at one of its 2 pure equilibria, not the mixed equilibria, which is sort of what we hoped would be true. Hofbauer and Sandholm show that there aren't any cycles in what are called potential games. So potential games are games we can transform into team problems by monkeying around with the payoffs. On the other hand, this continuous time best response dynamic does cycle in the following famous example of Shapley. So I'm going to show you the game on the next slide. So this continuous time process has a cycle. Okay. So I claim that corresponds to a discrete time system cycling slower and slower. And I have a question mark, why? How do I know it has to be cycling slower and slower in discrete time if the continuous time process has a cycle? Exactly. In order to get to continuous time, I had to do a time transformation. If we had a fixed length cycle in the discrete time, it'd be chattering super duper fast, in continuous time. It wouldn't be cycling. It'd be noise. Okay. So because continuous,
Can you get that?
huh?
Can you get that?
No, here, because the smoothness makes this impossible, because the play is continuous. The play would just smoothly to the past. The whole point, we can't, the whole approximation argument has troubles when this happens. We've ruled that out by assumption, okay, the chattering. So here, there are cycles in the continuous time, which means the discrete time is cycling slower and slower. In fact, it's cycling super slow. So here's the example. It's a very simple 3x3 game. Okay. And so I claim, so under exact fictitious play, with any priors at all, any weights, I claim what's going to happen, play will follow a best response cycle. Okay. So what do I mean? So we suppose the first thing that's played is here. beliefs are such that this is played for a while. If this is played long enough, player 2 should learn that player 1 is playing up. We'll think up is the most likely. Then player 2 should switch to right. So the best response cycle goes from here to here. We play that for a long time. Now player 1 realizes, oh, 2 is playing right. I should switch to here. Play that for a while, and player 2 realizes, oh, 1 is playing middle. I should play here, then we go here, then we go there. We never go here. Okay? So that's just telling you the actions that are played. How long do you spend in each region? So Shapley gave a direct proof that the time you spend in each region not only grows, it grows so quickly the time average of play does not converge. Okay? So remember this result. If the time averages converge, the limits correspond to Nash equilibria. Okay? They needn't converge because the limbs inf and limb sup needn't be the same. So Shapley has this direct, but maybe not so revealing proof that it doesn't happen. Maunder, Samet, Sela have an alternative proof that I think is more revealing about that leads to the same conclusion. But okay, so that tells us that at least in this game, if we wanted to compute the mixed equilibrium, which we can get by inspection, fictitious play is not such a great way for doing it. And Shapley's example in 1964 ended the early literature on fictitious play because they viewed this as a computational tool. It failed. Okay, we quit. Eric, you have? Let me set the stage a bit for what Sergio will do and get some motivation. Let's say a learning rule is consistent along a history if it does at least as well as you would get by maximizing against the time average of the history. Okay? Deterministic play is approximately consistent if the history satisfies this infrequent switching condition. But when it's not satisfied, players can do worse than maximizing against the time average. Like in my screwy example, right? People are getting 0 each day, and if they just mixed 50-50, which would be so the time average of opponent's play is 50-50, I can best respond to that by playing 50-50, or always by playing heads or whatever, and all of those would give me better than what I'm doing. Okay? Because players miscoordinate each day. So 2 properties you might want a learning rule to have. You might want it to be safe. You might want it to be the case that you almost surely get your min-max payoff, regardless of opponent's play. Note that's a non-Bayesian criterion. It's regardless of opponent's play. I'm not taking an expectation over prior. I'm just saying this is a non-Bayesian criterion you might like to impose on the agent's learning rule or on your own learning rule. A stronger condition we'll call universal consistency. No matter how your opponents play, you almost surely do as well as if you knew the frequency of opponent's play in advance. Not the order, but the frequency. Since utility of the best response to the actual frequency has to be at least min-max, because the actual frequency can't be worse than min-max, this universal consistency implies safety. Any Bayesian expects he will be safety consistent. He expects to do better than at least his min-max, given his beliefs. The universal part is it's not just with respect to your belief, it's uniformly over anything the opponent could be doing. In general, this requires mixing. Why? Because it's a worst case criterion. It has to be over any rule your opponent had. If you're playing matching pennies, using any deterministic rule to get your play, the worst case, your opponent knows your rule and beats you every day. So in general, we expect you will have to randomize to get this sort of consistency property. Let's say tomorrow, I think it's today. It's a question. Today. So what sort of randomization procedures guarantee universal consistency? This is something Sergio is going to be discussing. Okay. So I was afraid I was going too slow, so I sped up. So in fact, I have time to get to some of the extra stuff. So let me let me conclude with one little extension of the fictitious play literature. It's more recent. So the non-strategic behavior assumed in fictitious play, that you don't give up payoff to change what your opponent does tomorrow, doesn't make sense if there's only one agent per role. We need many people on each side for it to make sense. But the early results in this field, like Bonheim-Hirsch, Fudenberg-Krebs, assume there's only one agent per role. So what happens if we take seriously large populations? Many player ones, many player twos. Well, there's different ways we could do this, and our paper looks at 3 variants. I'm going to discuss one of them that we called asynchronous clocks. So it's a single population of agents. So it's a symmetric game. There's no player ones and player twos. There's just players. And each period will take 2 agents at random to play the game. And to start with, assume every pair of agents has the same probability. So uniform random matching. And when you get to play, you play a smooth best response to your beliefs, just like in smooth fictitious play. Afterwards, you update your assessment based on what you saw. But people who don't play don't get to see anything. So this is like learning from your own experience. And so what's going on with this one pair at a time, you wouldn't do that in the lab, but you could think of it's out in the field, and there's a Poisson clock going off at random intervals. People meet and play the game. Okay. Well, now, since different people only update when they play the game, only see their own behavior. First off, different people have different beliefs. Secondly, different people have different sized data sets. Just by random chance, one person might have been called 10 times, the other person 4 times. So the clocks are, this is what I mean by asynchronous clocks. In the lab, everyone can play equal number of times. So what we do is we show that none of this matters, and Bonheim-Hirsch's conclusions all extend, which I think is it's very good for the field of learning in games. It's maybe not so good for this paper, because then people say, oh, we knew that, and so what's the point? It's not surprising. Structure of the argument, we derive a limit continuous time deterministic system with heterogeneous beliefs. Each agent can have different beliefs, using the stochastic approximation machinery that I showed you. Then argue that the system converges to situations where everyone has the same beliefs. And that you can, when you analyze convergence and local stability and so on the smaller subspace where people have the same beliefs, all those conclusions extend to the bigger space. So it's perfectly fine to work with the restricted model of one agent per side. So just a little bit about how we do this. Let kappa bar of I and n be the sum of the weights that player I has on the different strategies. So it's how many times player I has played. At its period n, player I, different players will have played different amounts of time, because different people are called each day. So in terms of how much you update your beliefs, you update not by 1 over n, but by 1 over kappa bar. Because it depends on your data set, is how much impact the next observation has. Okay. Now, the standard argument was based on a sort of a step size of 1 over t, or in this notation 1 over n. How are we going to get from this setting with different clocks to 1 clock? So this is a trick that's been used many times before, and you may find useful in the future. We have a model like this heterogeneous learning model, but doesn't fit the assumptions on our standard model with the natural state space. Different people have different clocks. Oh no, isn't that bad? Well, we can fix this problem by working on a bigger model that does meet the standard assumptions. We have a great big model with a big clock that ticks off whenever anyone plays, and then use that to drive the individual clocks. So you don't meet the assumption you want on a small state space. You can probably meet the assumption if you add enough stuff into the state space.
So the story might look like this. So we have population with heterogeneous clocks. At each time, at each day, 2 people meet and synchronize their clocks. Then in all population, the clocks will be synchronized in the limit.
Sure, that's not this story. But yes, that'll be different if people said, I say, how often have you played? How often? But instead of what does it mean synchronizing clocks? Because here the clock this is a metaphor. It's more how big your data set is. So the clock, your personal clock, tells you how many data points you have, how much you update the next time you get a data point. Now, if every time people met, they pooled all their data, oh my, then yes, people would end up with the same data and the same clocks. That's not the assumption here. Okay, so now we have to work on a bigger state space. This is the kind of state space we had before, tracking the fraction of times that player I has played each action. And this is the evolution of our auxiliary variable. How often player I is played. There's m players, 2 people play each day. An expectation, player I should play fraction 2 over m of a time. He doesn't quite play that often, so this is tracking how often player I is played. His clock. What is y? I talked about the trick, but not the letter. So y is just the ratio between player I's data set, how often player I is played, and how many periods there have been total. Okay. Let's look at the inner part. Okay. So what has player I seen? No. What has player I been doing? Here's what player I has been doing so far. Data I of t, the average of player I's play. What will player I sorry. This is what player I has seen. This is player I's observations of other people, not what player I has done. So it's player I's observations of play. It's a vector. How often have I seen my opponent play A, B, and C? This is what I've seen so far. There's m minus 1 other people. I'm equally likely to play anyone. What's the expected thing I'll see when I play someone? It's the best response of them to what they have seen. So this is the average play of my next opponent. So this is, on average, what happens to what I see when I get to play. I don't get to play every day. How often do I play? Well, on average, I'd play 2 over m if life was perfect, but sorry. On average, I'm not explaining well. Okay, too much algebra, not enough explanation. This is a 2-dimensional system. Details don't matter. Fine. We want to relate this to the Benheim-Hirsch system that we had before. Okay. And more jargon. Maybe I should just not try and do something this complicated in 10 minutes. And here's, sorry. I do want to get to that. So let me summarize this with less jargon. What this is saying is when you decipher it, is that in the long run, we end up with everyone playing an equal number of times. That's this. And everyone having the same beliefs. That's this. It's not surprising in a sense once you see it. Over and over, we're interacting with the same population. We're getting different draws from a common pool. You might think our beliefs all converge to being the same. So that's what this is saying. And we end up at something that's would have been predicted by Benheim and Hirsch in the system with only one agent per side. Sort of a heuristic for this that I have is if you have like the plane, and you first show that the plane converges to a line, the plane of a line converges to a point, you converge to a point. So the plane is the heterogeneous system. It converges to the line where people have the same beliefs. But Ivan Hirsch said on the line you converge to a point, so you converge to a point. So that's the story. And conversely, if a mixed equilibrium is unstable when people have the same beliefs, then it's unstable in the big system. So it's maybe wasn't obvious to us ahead of time. We thought maybe these cycles could be broken if we had lots of different agents interacting at different times. That would somehow break up the synchronization needed for cycles. It doesn't. The theorem says you used to have a stable cycle, you still have a stable cycle. Now the interesting thing, and the reason I wanted to put this paper up, even though it's a bit complicated, is there is an open question we haven't solved. Okay, our base model is everyone has the same clock. We can extend this to the case where the probability that different people play differs if it's not too different. Okay? Let Pij be the probability we pair that I and j get to play. And that needn't be the same for each pair of agents. Okay? And then we have a measure that says if these Pijs aren't too different, everything's the same. But our measure rules out all the interesting network structures. So you can think of people on a circle only playing with your neighbors. So then the interaction of player 1 and player 2 is very high. Interaction of 1 and player 10 is maybe almost never. That fails this condition. So then it's possible that maybe we don't converge to all having the same beliefs. And you could have little islands where some people are coordinating on A and some on B and some strange stuff happening on the edges. There's not good results for this. Okay, so in terms of open questions in this literature, it's to look at large population models, sort of on networks or some sort of asymmetric interaction probabilities, and see what happens. And I've 5 minutes left, but please, questions?
On the previous slide, where you don't rule out cycles.
Sorry, where I don't rule out, sorry?
You thought you might be able to.
Well, yes.
I was wondering whether that finding is connected to the one that Sergio was talking about yesterday, that you can always, if you use what he was calling natural dynamics, you can't guarantee convergence.
Yes. It's related. These dynamics are definitely uncoupled. I believe they're natural in his sense. So that means we couldn't guarantee convergence. Now, because we're in dimension more than 2, the stable cycle could have become chaotic or something. So just because it's not converging, we don't know, but it's still stable. Or it might be that if we had multiple stable cycles, some die and some live, so all sorts of things could have, saying every single stable cycle is still stable. So it's a bit of a sharper conclusion, but what you're pointing out is maybe this is not surprising in view of that fact, and that's fair, that's right. And that's a general point, right? I mean, if you take learning comes from some dynamic process seriously, there's no reason to, expect equilibrium. The only reason, so there are rules that will give equilibrium, and then again, I don't know how much Sergio talked about this debate between Hartmass-Kalal and Foster-Young and so on about how to define what convergence is and whether being near equilibrium most of the time is versus. So the impossibility results rely strongly on that, and if you're prepared, yes. Right, so Young has results that get you, 1 minus epsilon of a time, you're at equilibrium, and every million years you go away for a while, and you come back. And for me, that's good enough. That's not, these sorts of systems really don't have that, because the Young sort of systems, some have a persistent random term, so they're ergodic. And here we're having all the random terms are dying out to have a continuous time approximation. So it's, but yeah, at a conceptual level, that's right. I mean, he's saying you shouldn't expect convergence, and I'm saying we have examples without convergence, and this thing doesn't break it. And sure, that's now what sort of we don't know about that many different games, but we know some simple economic games of convergence. We have like Shapley's counterexample was pretty much constructed to not get to be bad. In practice, how big an issue is this? We simply don't have. I don't have a sense of how common these cycles are. It'd be nice to know more. But I should let the people have a break to get ready for the next round. And I apologize for having glossed over the technical details here, but it is, I've correctly said on the slides, I think, it's just going to probably take more time and effort than it's worth to pin it down right now in class. So I will see you tomorrow. I'll talk about active learning in extensive form games. Thanks. Well, all except for the part where I